The Iron Bridge sits within the picturesque Severn Gorge. It's the first ever freestanding structure made entirely of metal, and as such, it's a symbol for the birth of the modern world. This landscape has always been one of industry. The bridge provided a great opportunity to link up either side of the river. They didn't have to build it out of iron, but this is a landscape of iron founders, and they really want to demonstrate to the world what it is they could do. Without the technology that went to build the bridge, you wouldn't have the railways, you wouldn't have skyscrapers. Go to New York, what you see there are the great-great-grandchildren of this structure. The bridge is now almost 240 years old. It's been an icon of the Industrial Revolution for centuries, and every generation has done its bit to safeguard it. Now it's our turn.
We at English Heritage want to be able to secure the Iron Bridge for years to come. It is suffering through the ravages of time. That's why we're embarking on an ambitious conservation project. The main elements of the repairs are to the ironwork structure itself, to the single span, both addressing some of the casting imperfections from when it was first constructed, and also damage incurred over the years due to ground movement. The ironwork will then be repainted, primarily to protect it from the elements. And it's also about the masonry conservation, to the piers, to the abutments. It's the road surfacing and the decking. This is a huge project costing £3.6 million. We've raised money towards that, but we're still short of the target. And we need the public's help to raise £25,000 to complete the work.
It's the final push. We're almost there. We need the support of the public to help us achieve our ambitions and to ensure that this fantastic monument of the Industrial Revolution is here for generations to come.
That brings you a good introduction to the Iron Bridge. I'm not going to talk about that initially. I'm actually going to talk about what I do. So I'm a conservation engineer. I'm a chartered civil engineer, but I also do a lot of conservation. And I just wanted to highlight there is an accreditation system for engineers involved in conservation. It's a jointly run scheme by the Institution of Civil Engineers and the Institution of Structural Engineers. And we have, I think, probably over 60 or 70 engineers on it. And that does open you up to all sorts of opportunities. I'm very lucky that I work at a number of cathedrals, castles, and other really important structures. A few of the other types of bridges I've worked on. At the top left, we have a replacement timber bridge, Chinese bridge, which was built in 1740s, had disappeared, and we recreated it from information. On the right, a new bridge, but in a historic landscape setting in Oxford at Christchurch. At the bottom, an old railway bridge at Great Yarmouth, and on the right, a pier, the earliest cast iron pier in the world, allegedly. So they're the types of project as a conservation engineer that you can be opened up to. But of course, working on the Iron Bridge, 1777 to 1780, and really one of the key triggers for the Industrial Revolution. So as an engineer, you can't really be asked to be involved in anything better. A few key notes in terms of who is involved. We have the client, who was English Heritage. Ourselves were appointed after a tender as lead consultants. Architects to help with some of the elements, particularly the masonry repairs and road surfacing. Quantity surveyors, Preston Starkey. Historic England played a very important part, and of course working very closely with our principal contractor, Tazica Industrial. So one of the things about the Iron Bridge is it's a scheduled ancient monument, and if you're not familiar with that, that's actually one step up from a Grade 1 listed building. Essentially, you can't do anything to it. You couldn't put a sign up on it without scheduled ancient monument consent. A few of the key facts in terms of what the main objectives for the project was. To conserve the fabric of the bridge and prevent the loss of historic material in accordance with conservation principles. So one of the unique things about Iron Bridge is actually almost all the material that is there is the original material, which is really unusual. About 1,700 components, So it's it's a kit of parts, and it was actually built using carpentry technology. So it's mortised and tenoned, because they weren't familiar with iron steel structures. To clean the ironwork and remove corrosion products, so the metalwork could be painted. To maintain and improve the bridge's structural integrity by replacing missing components and reinforcing others where necessary. And again, one of the key principles of conservation work is wherever possible, we want to make that work reversible. So in the future, we can come and undo that if there's a better technique for doing it then. To renew the deck surface and return it back to something which is more traditional and what we believe was historically there. And to remove some of the utility services which are below the deck surface. And to make best use of the scaffolding, because obviously the scaffolding is a key and expensive element of the works, and you've got to make the key use of it whilst it's there. However, before we were appointed, there was a whole phase, a number of years, 3 or 4 years, of assessment of the structure by Ramboll. This was the first time that actually the bridge had been fully looked at, finite element analysis, and laser scanned. So that mapped as many of the defects as we knew existed. There was about 100. That's cracks, and as you saw in the video at the beginning, partly related to ground movements. Basically, the gorge is moving in. The outcome of that was guidance on repair options, loading guidance. Bear in mind that this had been used for traffic. So up until about 1927, when the traffic was removed, it always had traffic running over it. Monitoring regimes to understand if the movement to the gorge was causing any further effects. And then summaries, feasibility study for the repairs. But we had quite a lot of other information that we had to pick up on as well. A conservation management plan. If you're not familiar with that, that is a document which is meant to tell you about the history, the significance of the structure, and meant to guide you in terms of the policies for the repair, using standard ones such as low intervention and reversible. There was a good repair phase in 1999 by English Heritage, and the chief engineer at the time was a friend of ours and lives quite close to me, so I was able to access his information. Archaeological reports, so every time anything happens to the bridge, as Jason well knows now, you have to have archaeologists involved, so they record everything you do. Underwater bridge strut. So because of the movement in the gorge, in the 70s, it was decided to try and rectify this, or not rectify it, but prevent it happening anymore. So they actually put a large concrete underwater strut below ground, and since then it's been monitored, and in fact there is no more movement at this time. Investigation reports, and bear in mind these go back over probably 40 years. It's a huge amount of information to assess. Paint adhesion technical reports, railings reports, they'd been strengthened with carbon fibre some years ago. And talking to those who've actually worked on the bridge. It's amazing how much useful information you can get from people who've been involved with it in the past. So we had to evaluate all that existing information, which is a long exercise in its own right. And we also had very limited access to get on the bridge. And even during the course of the investigations by Ramboll, they had roped access to the outside, but they couldn't get to any of the ribs on the inside. So there was still a lot of the bridge that hadn't been seen. So we only had the bridge deck and low levels accessible, plus we did manage to get a cherry picker just to some of the edges. Another key aspect, and something that we'd put into our tender document, is that we felt this was a good opportunity to actually get public engagement. Now, what can that mean? Well, we felt that actually it would be nice if the public could actually get on the scaffold in a limited way and get this unique opportunity of actually seeing below the deck structure, see the works going on. And seeing as it was English Heritage Conservation in Action Year, this was felt to be really important. And just if the... There is actually our access walkway that we put alongside it. And over here is that in completion. And here are our happy people having a look through. Also built into the contract was a number of hard hat tours. So I think, Jason, there's about 40 of them? So about 40 hard hat tours. So Duncan, who was the site agent, had it off to a T by the end of the project. But obviously it bit into his time quite significantly. New castings. So there was a few new castings we needed, particularly the deck wedges. So structurally we have a number of ribs, arches running across. We then have deck plates on top, and the deck plates are actually wedged down onto the ribs to provide lateral stability. We then looked at the condition as best we could based on the existing information pre-start with regards to the movement of the arches, which had caused deformation. So basically some of the cast iron members had bent. Lots of fractures had occurred at key areas, and quite significant ones. And corrosion, a big part of it, and at the top there you can see some of the 1902 repair straps. So that's another thing that came clear fairly early on, that there was a whole series of later repairs. It's recorded the first repairs were only 3 years after it was finished, and that's due to the gorge movement. And the other key one was water ingress through the deck sheets. So a few images. You can see our concrete strut that was put below. We had a diver survey carried out to check that that was still okay and there was no scouring around it. And that's a historic image of the reinforcement when they were creating it. And there we have a buckled OG arch to one edge. And here is the evidence of the corrosion. So we had these pockets of corrosion building up, and as you know, cast iron is actually a very brittle material. So once you get this corrosion product building up and increasing and jacking, it essentially gets to a position where the cast iron fails. So very significant corrosion of wrought iron or steel bars, the 1902, but then damage to the cast iron. You can see that element is cracked. One particular concern was the deck end plates. So these are continuous plates which run across the bridge, and they have these lobes at the bottom. But as soon as you get any corrosion build-up at the back of that lobe, basically it jacks the lobe off. So we've had several which had fallen, and others which were actually found to be loose once we got the scaffold up. And again, an example of the types of fractures we were finding in the cast iron. And here's an early repair. So ultimately, we had to get to a point where we decided what we were going to do. And because we couldn't get access onto the bridge or below the bridge, we had to come up with a whole series of repairs based on the investigations, which were then tendered. But it was then only once we got the scaffold up that we could actually truly establish what repairs were needed. And I'm going to hand over to Jason now.
Yeah, just like Ed, myself and obviously all the project team at TI really felt privileged that we've been entrusted with the conservation of such an iconic structure. And as Ed outlined the majority of the scope of works, we also found ourselves facing a number of operational constraints that obviously impacted on the delivery of the scheme as we actually progressed. For me personally as an engineer, this was probably my first real conservation project. I'm usually restoring and repairing bridges, so sometimes it's quite frustrating not to physically fix it, but just to hold it in place, and that was quite a big learning curve that myself and the whole of the project team had to get used to throughout the project cycle. We had to keep the bridge fully open to operational pedestrian traffic over the bridge and obviously watercourse users. And if you ever go there over a weekend, you really appreciate what a visitor attraction this structure actually is, with a number of visitors that descend in such a small valley. The observation platform that Ed touched on will give a bit more detail as to the problems that we faced in delivering that. It is actually in quite a steep valley with heavily built up residential area, so we were restricted with the actual operational hours that we could undertake the physical works. And as Ed inferred, we were constantly monitored by archaeologists We usually grip blast these structures. I think these guys wanted us to do it with a toothbrush. The amount of actually intrinsic investigation they wanted to do at every phase of the works that we were undertaking. The first key thing for ourselves was obviously the temporary works, and we had to take that up to the full design. The clear span itself is 30 metres, and obviously we had to reduce that down to the capacity of the unit beams, which was around 18, so we did that via a staged approach, but we couldn't actually impose any loads on the brittle cast iron structure itself, so we actually had to build everything up from beams at the base, and then obviously staggered up so that we allowed to get this unit beam across. Now we lifted those in with crane in a day's blockade of the road closure that we had to have adjacent to the track. And the entire scaffold itself had to accommodate for a cantilevered walkway. Now the cantilevered walkway itself, whilst it was taking pedestrian traffic, we couldn't accommodate the normal pedestrian loads. Obviously limited by the scaffold constraints, so we had to reduce that to a 2.5 kilonewton loading, and we did that via having volunteer guards at each end of the walkway, restricting the number of people that could utilise it at any one time. So we actually restricted the global loading of the walkway in order to integrate it into the final design. The scaffold itself actually took 3 months to build, which, when you put it in context, in 1779, when the entire main span structure was built, that actually took less than 3 months. And obviously, knowing how difficult it was to plan and deliver that with modern craneage, it was really an eye-opener to understand how they'd actually built that structure in a 3-month window. It wasn't actually until 1997 that a watercolour was discovered in Sweden by Elias Martin, who was an artist, and it actually showed the bridge being erected using derrick poles to get the main ribs in place before they were connected at the crown bearer. And the time team, Tony Robinson and his crew, reenacted it as a 1 in 10 scale model back in 2010, which was quite interesting. But given the amount of time it took to do the scaffolding, it certainly brought it to light how quickly it was erected all back then. Just as a brief nomenclature of the structure itself, it's quite simple in its design with standard stanchion verticals. It's made up of 5 ribs in width that span a 7 metre width. It's made up by a lower rib, which is actually the main part of the structure, an intermediate rib and an upper rib, and these are spaced by radials. And you've got some of the horizontal bracings. The cast iron deck is made in metre-wide slabs that span the full 7 metres and have the lobes over the top. There's nothing sexy or innovative we could do in relation to the steelwork design. Obviously, Ed and his team had already designed that to maintain as much of the existing fabric as possible. So the repairs are quite basic in their format. They are there purely just to hold the fabric to prevent any future movement. So there was very little innovation that we could bring to that. The remainder of the work obviously was to the brickwork repairs and obviously to address the water seepage through the existing deck by putting a waterproofing system on and replacing the deck in its entirety. As part of the initial concept behind the tendered works was to spot blast the structure, so that was purely to remove corrosion in the worst case scenarios. However, we found as we started to do that work that there was going to be quite a lot of problematic areas with the interfaces where we was leaving existing coating. So we managed to value engineer the project by negating some of the areas that were down for blasting, like the road deck, which we were going to be covering with a waterproofing membrane, and actually went with a full SA 2.5 grit blast to remove as much of the existing coating as possible. So there you will see on the left, obviously when it was first flash blasted before we went back over it, and obviously one of the radials over on the right. Now you'll see from those pictures the level of porosity in the early cast iron. Obviously this was one of the first attempts. And obviously you can really appreciate the level of holes that were actually in the ironwork, some of which you could physically get your fist and your hand into. So in order to get a protective coating on those to prevent any further corrosion was always going to be somewhat problematic. So that brought us onto the painting concept. It was a 3-coat paint system, 2 coats of an epoxy and an acrylic urethane top coat for gloss retention. You can see each of those were governed by an additional stripe coat. For the eagle-eyed among you, the picture there on the right, that is not an intermediate coat, that is the finished article, which has somewhat changed from the battleship grey that everybody has known the bridge to be over the centuries. The reason that it was changed to a red oxide is twofold. Predominantly, some of the original images of the bridge obviously showed it in a red, and when we went back to with the archaeologists to pick away at the various layers over the years, we actually found that we believe the original colour of the structure was a red oxide. From a painting contractor, that was great news, because a lot of those areas where you had the large porosity holes, we can't guarantee that we can get sufficient application of the coat to prevent any further seepage when we used to strip the scaffold. So what we didn't want to do is hand over a lovely grey bridge that was seeping brown or red rust stainings from areas we couldn't actually access before we'd even taken the scaffold down. So the reason that it's got one of the attributes of it going back in red is that will significantly negate any future visual impairments that will bring upon. That brings us on to the steelwork or the ironwork repairs themselves. And as we mentioned, these are really just holding repairs. As you can see by the damaged radial, it's obviously cracked. A number of those had also cracked and moved laterally, as well as obviously just opening up on the vertical gap. The remedial technique was to obviously overplate these with stainless steel bars and a neoprene strip, obviously between the cast iron and the new steel plates, that was to sandwich them together. And like I inferred before earlier, as an engineer, you would think if there's a little bit of lateral movement, you'd basically just sandwich it back together, but that didn't tell the history and the story of the structure. So even where they'd moved laterally, we put backer plates on alternate sides to actually leave that lateral movement in, so that it told the story of the bridge. And as Ed inferred, if an alternative technique was to be found in years to come, that could be easily adopted. The lobe repairs themselves, again, very, very basic in principle and fully removable if the case were ever to come across. These were initially made in an MDF material, each individually templated to every repair that had been undertaken, once we removed all the rust jacking from the rear of these lobes. And obviously they're just held in place by a small bracket and a grub screw arrangement to the rear, so they can be easily taken off in the future. These were mild steel brackets that we had just to hold the mortise and tenon joints, obviously to prevent any further movement, and there was quite a number of those throughout the structure where fractures had occurred. And again, just as a belt and braces approach, we're fairly confident that the movement has been stopped and by the gorge beam that's been placed under the water. And this really is just a belt and braces to stop anything from falling off the structure. A number of these repairs were required where obviously the arch ribs pass through the vertical braces, and again it's quite a simple technique of just bracing these together and holding them to prevent any further movement going forward. This probably was one of the only repairs that actually necessitated a positive intervention where we actually drilled into the structure itself. The actual deck plates are continuous along the full length of the structure. They were slid out over the ribs once the ribs had been put into place. And as the lobe obviously overhangs, a number of these have actually fallen off. A 30-metre section actually fell off into the river in the 20s. So a number of these have already been repaired, where the rusting jacking has actually forced the lobe to crack the end of the cantilever deck off. Where the remainder of them were all cracked at the ends, we've actually installed new plates and bolted through the deck to hold that in place to prevent any further movement. 2 actually fell off whilst we were blasting the structure. We had to actually put in place a number of temporary works to hold the remainder in place to safeguard the workforce as we was undertaking the contract. As you can see there, the main beam itself is obviously fractured, and that was the case in a number of locations, but those were all long-standing fractures. So again, just a quite simple plate repair to hold that and prevent any further movement over the years. As Ed inferred, the majority of the ironwork repairs were to the deck wedges that obviously prevent the lateral movement of the ribs where they connect with the main deck. There were 347 of those in total, every single one individual. The reason for that is the ribs have moved obviously both vertically and laterally. So the idea was we had to remove the existing one, put a sand mould in every single location, file that to shape, and then send it to the foundry to have each individual one made. And then even when they came back on site, this sometimes needed slight modification to get a real tight fit. And we've got a little video at the end for those who've never been in a foundry to show how those were actually made in practice. And another element of the works was obviously to remove the existing deck surfacing. That had been replaced with heavy concrete and tarmac, again in the 50s. And it had a number of redundant services, or services we got made redundant with stakeholder involvement as part of the project. There was also a number of large 6-inch cast iron mains with large collars on them that had obviously resulted in the surface itself being raised over the years. So we took that back down to the original deck to obviously facilitate the deck wedge replacement. We installed a loose laid waterproofing system that was sandwiched in 2 protective layers, and rather than reinstate the deck utilising conventional techniques, we used a light aggregate concrete to reduce as much of the dead load of the structure as possible, and then just replace that with a very, very thin bearing and wearing course of tarmac before obviously dressing that with stone and chip, which was obviously comparable, which was what was there before. And obviously we negotiated with Southern Trent Water to replace the water mains across the bridge with a HDPE, which removed the collars that were on the existing cast iron sections, and that allowed us to drop the deck, again reducing the dead load of the structure. This is a brief video just to conclude on that was taken for BBC Breakfast, and this takes you into the foundry and gives you a little bit more insight as to some of the repairs that we undertook.
World's first iron bridge, built almost 240 years ago in Shropshire, is undergoing a multi-million-pound conservation project. Breakfast's John Maguire went along to take a look.
What we're seeing here is really a symbol of how the Industrial Revolution helped to create the modern world. This shows innovation, it shows engineering, technology, and it shows something that's really stood the test of time.
But at the moment, the iron bridge that joined 2 riverbanks to create a town that took its name isn't on show itself. At the grand old age of 239, it's undergoing a major £3.6 million conservation project. Iron is famously strong, but can crack if bent or twisted. And as the ground has moved, the bridge has been forced upwards by as much as 4 inches in places. Now we're on top of the bridge, and this gives you a really good idea of what's been happening here. They've dug down through the road surface to expose these iron plates. Each one would weigh several tons. But just look here, there's a huge crack in there. This piece could fall off at any time, so that's the type of problem that needs to be fixed. Despite the current major works, it remains open to pedestrians. And English Heritage will soon open these walkways to allow visitors to see close up what's going on below the deck.
From repairing broken components, cleaning things down, painting, everything that happens to the bridge, as far as possible, we'll make sure it's accessible to the public.
We've been given special access inside. Picking your way through the bones of what feels like the bridge's rib cage, you get a real sense of the task at hand. Old paint and rust is being blasted off in conditions that bring to mind the black air that would have filled the gorge at the height of the Industrial Revolution. No modern protective clothing for them. This isn't restoration, it's conservation.
We don't want to find ourselves thinking that we've done a great job and then in 30 years' time we make a huge problem for the people that come after us and who then spend their time trying to undo what we did. So we make sure that all of our interventions are reversible.
The bridge's builder, Abraham Darby III, was a visionary, a revolutionary. No one had used this wondrous material, iron, in this way before. And now, 2.5 centuries later, these wedges are being recreated in one of the country's few remaining iron foundries.
We are absolutely in awe of the fact that they had none of the facilities that we've got now. They were pioneers in their day, having to create their whole infrastructure to support the melting of metal in a way that was totally on the edge. How on earth did they manage it?
Standing here watching these masters at work, using techniques similar to their forebears, the centuries fall away. When the Iron Bridge is unveiled once again in the autumn, it will have a new paint job and a renewed understanding of how it was built. Its place in history is irrefutable, and this major project will ensure its place in the future. John Maguire, BBC News, Shropshire.
I hope that gives you a good oversight of the works that we've just recently completed, and open to any questions.